Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on random signal theory. In this video, we start a new chapter, chapter 4, continuous random variables. In the previous chapter, we talked about discrete random variables, those random variables x that take values from a discrete set of numbers. In this chapter, we will talk about continuous random variables. So what is a continuous random variable? A continuous random variable takes values from a range of numbers as opposed to a discrete set of numbers. The continuous random variable takes values from a range of numbers. That range of numbers could be finite or infinite, but in both cases, the variable x takes values from a range of numbers. Let's look at this simple example. So if we have variable x that takes values at random from the range from 0 to 1, so x could be anything from 0 to 1. This is obviously a continuous random variable. It is different from the discrete random variable x that would take values, for instance, 0 or 1. So the set 0 or 1, but here x could take any value from 0 to 1. So in this case, x takes values from a finite range of numbers between 0 and 1, although the values of x themselves, the values of the variable x itself could be infinitely many, because from 0 to 1, yes, the range is finite between 0 and 1, but we have infinitely many different values between 0 and 1. So this is a continuous range. Another example, let x denote the measured thickness of a wire. So you are measuring a wire. I give you a thin wire and a measuring tool, and I ask you what is the thickness of this wire, how thick is this wire. Then the answer that you can give me, it could be a random number that could be any positive value, so anything greater than 0, let's say. So in that case, x is a random variable, is a continuous random variable that takes values in the range greater than or equal to 0. So all values greater than or equal to 0. Bottom line, continuous random variables take values from a range of numbers, so a range like between 0 and 1, or greater than or equal to 1, or between 1 and 5, but the full range between 1 and 5. So this is a continuous random variable. Of course, the continuous random variable has also a probability function. In the discrete random variable case, we call the probability function the probability mass function. But in the case of a continuous random variable, we will call the probability function a probability density function, and we will elaborate more on that in the following slides. So the probability density function, like any probability function, has the basic properties. So first of all, since probabilities cannot be negative, so the probability density function is greater than or equal to 0. It cannot be negative. And since the sum of all probabilities equal to 1, so basically the summation of all function values is equal to 1. However, in the continuous case, if you want to do a summation over a continuous range, that summation turns into an integration, as you know. So the integral over all values of the variable x from minus infinity to infinity in general is equal to 1. So this condition here is equivalent to the discrete condition of the summation of all function values is equal to 1. So bottom line, the sum of all probabilities is equal to 1. And if you would like to sum all values f of x, and the values of x are actually continuous, so this summation will turn into an integration from minus infinity to infinity in general. Now, what is the role of this function f of x? This probability density function f of x can be used to calculate a probability like this. So if we have a random variable x, we will see an example in the next slide. If we have a random variable x, and that random variable x is continuous, it exists over a continuous range, and it has a probability function, a probability density function f of x. And we would like to calculate what is the probability that this variable is greater than or equal to a and less than or equal to b. In the discrete case, so that we have an analogy, in the discrete case, if we needed to calculate a probability like this, what did we do? We added all probabilities from a to b. In the continuous case, we're doing the same thing. We are adding all probabilities, so we add all function values from a until b, but because the variable is continuous, so that summation, that addition, turns into an integral from a to b of the function f of x dx. So the probability density function, if we do an integration between values a and b, it gives you the probability that our variable is between a and b. So after a and before b, greater than or equal to a and less than or equal to b. And since it's a limited integral, since we're integrating a function from a until b, it is equivalently also the area under the curve. So if you draw f of x, it would be that probability, or this integral is also equivalent to the area under the function from a until b. Let's look at my illustration here, because we have an important point to make so that you don't get confused. As an example, let's talk about a specific example. We have a random variable x which exists between 0 and 1. So our variable x is between 0 and 1. Our x variable can be anything between 0 and 1. So 0 and 0.0001 and 0.1987 and so on. So our variable x could be anything between 0 and 1, with probabilities that are reflected by the probability density function f of x is equal to 3x squared. Let's look at this figure here. So on the x-axis, we have the variable values, obviously from 0 to 1. And on the y-axis, we have the probability function f of x. And if you draw this function, it would be increasing like this. And we know that the variable exists between 0 and 1. So this is the probability density function here. Between 0 and 1, it's a quadratic curve, 3x squared. Now, let me ask you the following. What is the probability that x equals to half, like in the middle of this range? What is the probability that x equals to half? One common mistake here is that you would try to substitute with a half. This does not work in the continuous random variable case. In the discrete case, yes, we substitute, and the probability that x equals to something has a value. That's why the probability function consists of discrete points, and that's why we call it a probability mass function. But here in the continuous case, this is a probability density function. A probability density function cannot be used to calculate the probability at a specific point. Let me try to justify this. If our variable x exists between 0 and 1, how many different values do we have between 0 and 1? In other words, how many different values can x take? Although it's from 0 to 1, so deliberately I'm choosing a small range, but in this small range, how many different values do we have for x? Infinitely many values, from 0.00001 until 0.999 and so on, and everything in between. These are infinitely many values. Since we have infinitely many possible values from 0 to 1, what is the probability that variable x hits exactly one particular value that's equal to 0? Not only the probability that x equals to half is equal to 0, the probability that x equals to anything, as long as we have a continuous variable, the probability that x is exactly equal to anything is equal to 0, and we cannot substitute here. Having said that, what is the purpose of this probability density function f of x? The purpose is to be able to calculate the probability that our variable is in a range. What is the probability that x is from a to b, that x lies between a and b, that x is greater than or equal to a and less than or equal to b? Here, what is the probability that x is between a and b? So what did we do in the discrete case to calculate a probability like this? We had to add all probabilities from a to b, and since we have a continuous variable, adding all probabilities becomes an integration. So we have to integrate all probabilities, all function values f of x from a to b. So we calculate this probability that x lies between a and b using the limited integral of the function f of x from a to b. More specifically, this limited integral would give you the probability that x is greater than or equal to a and less than or equal to b. If we drop the equal sign, it's still the same thing. It does not affect us. The equal sign does not affect us. Why does the equal sign not affect us? From this fact, the probability that x is equal to a exactly is equal to 0. And the probability that x is equal to b exactly is equal to 0. So having the equal signs or not having one of the equal signs here, so if we don't have the equal sign with the a, or if we don't have the equal sign with the b, or if we don't have the equal sign in both a and b, it is all the same. So the equal sign is insignificant in this continuous chapter. In the whole chapter 4, this equal sign does not matter. So x greater than or equal to something is the same as x greater than something, simply because the probability that x is equal to a or the probability that x is equal to b is equal to 0. So there's again, this integral is equivalent to the area under the curve. So the area under the curve. This is just another example. Imagine that we have random variable x here. On the x-axis, we have the different x values, and on the y-axis, we have the probability density function, f of x. And if you need to calculate the probability that x is between a and b, greater than a and less than b, it would be the integral of the function. It would be the integral of the function from a to b, which is equivalent to the area underneath the curve from a until b, the limited integral. On this slide, it is just that we stress on the fact that the equal sign is insignificant. So whether we need the probability that x is greater than or equal to x1 and less than or equal to x2, whether we don't have an equal sign, or here we don't have an equal sign, or in both we don't have an equal sign, all these statements are equivalent. Why? Simply because the probability that x equals to x1 or equals to x2 is equal to 0. Now we go to the first example in which we see how we can use this probability density function to calculate some probabilities. In this example also we have a context. We have an engineering context. So we say that the random variable x here, our random variable x, denotes the diameter of a hole drilled in a sheet metal component. So we have a factory that manufactures something, that manufactures an item, and this manufacturing process requires drilling a hole in a sheet of metal. We would like this diameter, we would like the diameter of the hole to be 12.5 millimeters. But because of some errors, sometimes we get bigger diameters, and that's why the actual diameter x has a probability function, f of x, which is given to be 20 e to the power of minus 20 x minus 10.5, 12.5 in the exponent. Again, 20 e to the power of minus 20 x minus 12.5, and this applies for x greater than or equal to 12.5. This is our variable x. It starts from 12.5 onwards, going possibly to infinity, and the probabilities for the different values are reflected by the probability density function. And this question here told us where is this variable coming from, which is not very necessary to answer the question. So here in this course, we're having a random variable x, which starts from 12.5 onwards. So the range for variable x is greater than or equal to 12.5, which is obviously continuous. And the function values, the probabilities for x are reflected by the probability density function 20 e to the power of minus 20 x minus 12.5. What is the question? The question is, what is the probability that the diameter turns out to be 12.6 or more? What is the probability that our variable x is greater than 12.5? Of course, if we have an equal sign, it will not change anything. As we explained to you earlier, we need the probability that x is greater than 12.6. So how do we solve this? We have to add all probabilities from 12.6 onwards. Again, in the continuous case, we have to do an integration from 12.6 until the end, since this goes to infinity. So it would be an integral from 12.6 until infinity, and we need to integrate the probability density function. So we need to integrate this function, 20 e to the power of minus 20 and so on. So that 20 is a constant. That's why I took it outside the integral, and we need to integrate this exponential function, this negative exponential function, e to the power of minus 20 x minus 12.5. What is the integral of this function? It's really easy. The integral of e to the power of x is the same, e to the power of x. Let's extend it. The integral of this exponential function is the same. So this is the integral, is the same. However, we have to divide by the derivative of what you see in the exponent, and the derivative is minus 20. This is the constant, minus 20. That's why we have to divide by minus 20, and this 20 in the numerator is just the constant that we copy as it is. So 20 as it is, and then the integral is the same as the exponential function, but divided by negative 20. Of course, it will cancel. We will have a negative sign here remaining. However, we still have the limits of the integration. So this line here, and then the lower limit is 12.6, and the upper limit is infinity. So how do we deal with this limit? We substitute with the upper limit first, and then we subtract the substitution with the lower limit. So let's put infinity. If we remove x and we substitute with infinity, we get e to the power of minus infinity, which is 0. e to the power of minus infinity is the same as 1 over e to the power of infinity, which is 0. And then we have a minus the substitution with 12.6. So we remove x and we put 12.6, so e to the power of minus 20. 12.6 minus 12.5. 12.6 minus 12.5 is 0.1. 0.1 times 20 is 2. We have a minus sign, so the answer is e to the power of minus 2. Of course, 0 minus something is just minus. With another minus, it becomes plus. So the answer is the answer is e to the power of minus 2, equivalently 0.135. Of course, this e is the Euler constant. Using the calculator, 0.135. So that is the probability that our variable x is greater than 12.6 or greater or equal to 12.6. So this figure just illustrates that we did an integral of the function from 12.6 until infinity, and that integral we just integrated to get the value which is equivalent to the area under the curve. So that area is definitely 0.135. Now a follow-up question. What is the probability that our variable x is between 12.5 and 12.6, greater than 12.5 and less than 12.6, which is basically here between 12.5 and 12.6. Of course, if we have this question from the beginning, we just need to integrate from 12.5 until 12.6 of the same function. So the same function here that we have integrated, the same integral, but the limits will be from 12.5 to 12.6. So the integral will look exactly the same, but the limits will be from 12.5 to 12.6. So we'll get a number here, and we'll get a number here. We have to subtract, and then we will get the value. So it can be easily shown that the answer to this integral, the solution to this limited integral, is 0.865. Of course, it is easy to notice that this 0.865 is actually 1 minus 0.135, which is the answer that we have obtained before. In part A of the question, so we can think of this as part A of the question, and this is part B of the question. In part A of the question, we obtained the probability from 12.6 onwards, which is this area under the curve, which turned out to be 0.135. We obtained it. Now, in the second part, we wanted this area, which has to be 1 minus the other area, simply because the sum of all probabilities is equal to 1. So as a matter of fact, if you try to integrate the function from 12.5 until infinity, you will get 1, which is this property here. The integral from the beginning until the end is equal to 1. So if you want to integrate this function here from, sorry, not this function, we're talking about this example. If you would like to integrate this function from the beginning until the end, so in general, it's from minus infinity to infinity. However, this variable starts from 12.5. So if you do the integral from 12.5 until infinity, it definitely is equal to 1. So that probability is just the complement of this probability. However, we could also obtain it from the first principle, so we just need to integrate from 12.5 to 12.6. Since we know that the total area under the curve is 1, we could have done also 1 minus the probability that we obtained earlier, and its equivalent, we get exactly the same answer. Now we move to the next concept. So we introduced the continuous random variable. It's a random variable x that basically takes values from a range of numbers. So the range from 0 to 1, or here, as in this example, it was the range from 12.5 onwards, from 12.5 to infinity. So we are dealing with a continuous range, a variable that takes values from a continuous range. We understand this concept. We also talked about the probability density function of a continuous random variable. That probability density function does not serve us to substitute to calculate probability that x equals to something. No, the probability that x equals to something, the probability that x equals to something is always 0. However, using the probability density function, we can calculate the probability that x is between two values, as in this example, or that x is greater than something, as in this example. So bottom line, the probability density function, we used it by integration. We integrated the probability density function to calculate probabilities. Now we have a new concept similar to the case of a discrete random variable. In the continuous random variable case, we also have a cumulative distribution function, the capital F of x. So what is the meaning of the cumulative distribution function? By definition, the cumulative distribution F of x is equal to the probability that our variable is less than or equal to value x. So far, until this point here, it's exactly the same definition as in the discrete case. However, in the continuous case, how do we calculate this probability? What is the probability that x is less than or equal to x? Basically, we have to add all values from the beginning until x, which is an integral from minus infinity in general, from minus infinity until x of our function f of x dx. Since we have an x in the limit here, we can also replace the x of the function with a u, f of u du. This is a dummy variable, so we're basically integrating the same function f of x. We are integrating the same function f of x, but we have an x in the limit. I think the best thing to do is to cover this using an example. So this is an example to find the cumulative distribution function, and I think also it's best if I cover this through my own illustrative slide. So we follow up on the same example that we have seen before. So we have a variable, a continuous variable x, which starts from 12.5. So x takes values from 12.5 onwards until infinity. In other words, x is simply greater than or equal to 12.5 going until infinity, and the probabilities for the different values of x are reflected by the probability density function f of x, which is given as 20 e to the power of minus 20 x minus 12.5, the same function that we have seen in the previous example. But in this question, we are asked to find the cumulative distribution function f of x, that capital F of x. What was the definition again of the cumulative distribution function? It was the probability that our variable x is less than or equal to value x. So far until this line, it's exactly the same as the definition in the discrete case. However, in the discrete case, the way to find this probability of x less than or equal to x was by doing addition. So we kept adding probabilities. But here in the continuous case, to get the probability that variable x is less than or equal to value x, we do that by integration. So as we have seen in the previous definition here, to get the cumulative distribution, we have to integrate our probability function, which is this function, from negative infinity to x in general. From negative infinity to x, because negative infinity is the beginning, as beginning as it gets, so there is nothing before negative infinity. Now, let me substitute with the function that we have. So the function is 20 e to the power of minus 20 x minus 12.5. So 20 is a constant coming outside, and then the exponential is inside. However, if we need to integrate from negative infinity for that specific example, you will see that we'll start the integration from 12.5, simply because our variable starts from 12.5. For any value less than 12.5, the variable does not exist, or equivalently, that function has a zero value. So even though we want to integrate from minus infinity to x, equivalently, and for this problem, we integrate from 12.5 until x of the function that we have integrated before. So what is the integral of this exponential function? It is the same, divided by the derivative of what you see in the exponent, which is negative 20. So divided by negative 20, and this is the 20, which stays the same. It is just a constant. So obviously, this will cancel, and we will left with a negative sign. However, we have to substitute with our limits. So the upper limit is x. When we substitute with x, x becomes x, so the function stays as it is, minus the substitution with the lower limit, 12.5. When we substitute with 12.5, we will have 12.5 minus 12.5, which is 0. Of course, 0 times anything is 0, and then e to the power of 0 is 1. That's why we see that function as it is when we substitute it with x minus 1. Of course, a negative side, so we can flip the order, and the answer becomes 1 minus e to the power of minus 20 times x minus 12.5. We are done. 90% done. This is the cumulative distribution function as a closed form expression, because in the continuous case, we do that by integration. Now, the main question is this the cumulative distribution function f of x for any value of x, or only for those values of x after 12.5? After 12.5, because before 12.5, the variable does not exist, or equivalently, all probabilities are equal to 0. So now, what just remains is to put the final answer. So as a final answer, the cumulative distribution function f of x will have two intervals. So it would be 0 here, f of x, capital F of x would be 0 for all x values before 12.5, and for all x greater than or equal to 12.5, it would be given by this function that we have just obtained. As a double check, you know 12.5 is in between these two intervals. When we substitute with 12.5 here, what do we get? 12.5 minus 12.5 is 0. So e to the power of 0 is 1. 1 minus 1 is 0. So 0 here and a 0 there. And basically, we have a piecewise continuous function. If you want to draw the whole function in both intervals, it will look like this. 12.5 is our point in the middle. Basically, that distinguishes between both intervals. So we have 0 before 12.5, and then from 12.5 onwards, the cumulative distribution function is given by this form: 1 minus the negative exponential. 1 minus a negative exponential is actually a positively increasing function, which looks like that, and it approaches 1 asymptotically. It approaches 1 asymptotically as x goes to infinity. If you want to double check on that as well, that can be easily done. What happens when x reaches infinity? When x approaches infinity, let's substitute infinity here instead of x. So e to the power of minus infinity is 0. 1 minus 0 is 1. So the whole function becomes 1. So the function will approach 1 asymptotically when x goes to infinity. And this is how our cumulative distribution function looks like. One more topic in this video before we finish, which is the mean and the variance of a continuous random variable. Again, a straightforward extension to the mean and the variance of a discrete random variable. The definition is exactly the same. The mean, the expected value of x, e of x, or mu. Again, it represents the average value of the variable x, or the expected value, or the mean value. And by definition, it is the summation of the x values times the corresponding probability. As in the discrete case, we added x times probability plus x times probability and so on, but this summation becomes an integration in the continuous case. So by definition, the expected value of x, or the mean value of x that we call mu, is the integral over all values of x in general from negative infinity to infinity of x times the function f of x dx. That's the mean. What about the variance? By definition, the variance has the same definition as in the discrete case. The variance of x is defined as the expected value of x minus mu square. So again, the variance is an indication of how far the different x values are from the mean, of course, squared, and then on expectation. The same equivalent form that we have seen in the discrete case applies. So this is equivalent to the expected of x squared minus mu squared. What is mu? Is what we have obtained in the expected value of x. So again, the expected value of x is the integration over all values of x in general from negative infinity to infinity of x times f of x dx. And the variance of x, the basic definition, is the expectation of x minus mu all square, or equivalently the expected value of x squared times mu squared, and mu here was obtained earlier using the expected function definition. What is the expected value of x squared? It's obviously an integral of x squared times f of x. So the expected of x was the integral of x times f of x dx. The expected of x squared is the integral of x squared times f of x dx. And in both cases, the integral is over all values of x from minus infinity to infinity in general. But if we have a specific function f of x, the integral might be a little bit different depending on how our variable x is defined. Now, let's look at an example. Again, continuing with the same example here, let's recall that our probability density function f of x was given as 20 e to the power of minus 20x minus 12.5, and the variable x is greater than or equal to 12.5. The question is, what is the expected value of this variable x, and what is the variance of this variable x? We just use the definitions. So the expected value is the integral of x times the function f of x dx from minus infinity to infinity. However, in our example, the variable starts from 12.5, so the integral is also from 12.5 until infinity, from 12.5 to infinity of x times the function dx. Here we have an x multiplied by e to the power of minus x, which requires by parts. So you see the details here, and we can obtain the final answer. Of course, if f of x is only a polynomial, if f of x is a polynomial multiplied by x, we also get a polynomial, and then the integral becomes very easy, and we don't need by parts at all. Now, if we need to get the variance of x for the same random variable x, we need to get the variance of x. Here, we can either use this original definition, or even better, the equivalent definition as we are used to. So the expected value of x squared minus mu squared. What is the expected value of x squared? It is that function f of x multiplied by x squared and then integrated from 12.5 to infinity. But once we get the value of the integral, we have to subtract mu squared, which is 12.55. However, we have to square it. What you see here is basically the use of the original definition x minus mu here. So x as a variable minus mu, which is 12.55, and then squared multiplied by f of x dx. But we are very used to using this equivalent definition, which is also easy to use, even easier. Now, one last definition, which is an extension of the mean, and we call it the mean of a function of a continuous random variable. Imagine that we would like to get the expected value, not of x itself, but the expected value of a function h of x. Like, what is the expected value of x squared? We have seen it here. What's the expected value of x squared? It is the integral of x squared times f of x, right? What would be the expected value of x cubed? It would be the integral of x cubed times f of x. What is the expected value of sine x, if you will? It would be the integral of sine x times f of x. And in the most general case, what is the expected value of any function h of x? It is the integral of the function h of x times the probability function f of x dx, and we have to integrate over all possible values of x. We have seen exactly the same slide in chapter 3 in the discrete random variable case. However, the only difference is that we have a summation, so it's exactly the same concept, exactly the same meaning, but with the only difference that the summation becomes an integration. And we leave you here and continue next time. Assalamu alaikum wa rahmatullah.